Hello everyone, Rukved Nakadia here. Welcome to torsionaltraining.com. Thank you very much for joining this course. I'm very excited to teach you this course and teach you about torsional analysis. I think it's a great way to learn vibration analysis in general. When I got started in this field, some of my first projects were in torsional analysis, and what I found in general that the industry doesn't like to teach torsional analysis right away to their younger engineers. They prefer to start with some classic linear vibration analysis and then teach torsional analysis a little later. But I got lucky where I started working. They taught me torsional analysis pretty early, and my personal experience has been that I've learned a lot about vibration analysis in general because of torsional analysis. So I'm hoping to make a slight impact in how the industry thinks about teaching torsional analysis with this course. So I'm really glad that you're joining me, and I sure hope that we can change some mindsets in the process by teaching torsional analysis early, and I bet that by the time you're through this course, not only will you feel comfortable about torsional analysis in general, but you'll also feel comfortable about vibration analysis in general. So let's hope for the best, and thanks again for joining the course, and let's get started. So this is module 1, lesson 1, torsional vibration theory. Now my plan really is not to make this an intensely theoretical course. A lot of you have signed up this course because they want to learn how to apply torsional analysis with respect to using Dyrobes, or in that matter with respect to modeling torsional analysis in general. So I'll get to the Dyrobes part as soon as I can. So bear with me while I get through some of this basic theoretical stuff, and once I do, we will start by modeling a very simple shaft in this module itself. So one thing that's really important about torsional analysis is understanding the differences between linear vibration, which is right here, and torsional vibration. So with linear vibration and torsional vibration, they're essentially the same thing, except how the specific mass or the specific body that we're studying, how it vibrates. So in the case of linear vibration, you have vibration that is linear in nature, and in torsional vibration, what you have is this twist in vibration. But as far as modeling goes, it's about the same. While in linear vibration you have a mass and you have a spring which has a stiffness, in torsional vibration the equivalent of a mass is your polar inertia, and the equivalent of your stiffness or your spring is your torsional stiffness or your torsional spring. So really, as far as understanding the differences between the two, there really isn't much different. The equations have the same form. It's just that in linear vibration you consider mass, and in torsional vibration you can consider inertia. In linear vibration you consider stiffness, or K, spring constant. In torsional vibration you consider torsional stiffness. So nothing very different about the two. Now the one important thing about torsional vibration versus linear vibration is essentially the coordinate that we're using. In linear vibration, the classic coordinate that we use is x for linear displacement, and in torsional vibration we consider angles. So really the coordinate that we use, the generalized coordinate, is theta. If you recall classic physics, F is equal to k x, so solving for x, you have force divided by your stiffness. Similarly, in order to solve for theta, you have your applied torque divided by your torsional stiffness. So again, there really isn't much difference mathematically between the two. Of course, as far as physics goes, the displacement is in the linear direction, while in torsional the displacement is in the angular direction. But other than that, there's no difference mathematically. Now, just as an exposition of what the differences are, if you look at the mathematical model of a linear system, the classic vibrations equation is mx double dot plus cx dot plus kx equal to the applied sinusoidal force. So what you have, where x double dot is your acceleration, your x dot is your velocity, and x is your displacement, c is your damping ratio, k is your spring constant or your stiffness. Similarly, on the torsional side, you have your polar inertia, which is equivalent to your mass. Instead of your coordinate being x, you now have your coordinate in terms of angles. So in terms of theta, your your linear velocity is now replaced by your angular velocity, and your linear displacement is replaced with your angular displacement. Your mass dashpot here is now replaced with your torsional damping, and your spring constant is replaced by your torsional stiffness. Again, your applied force is F sine omega t, which is a sinusoidal force. In this case, your applied torque is important, and it's sinusoidally applied torque. So if you solve these two differential equations, your steady state response in your mathematical system, which is your x with respect to time, is in this general form. And similarly, again, your steady state response in your torsional system is in this general form. So you can see that really there is no truly mathematically any difference between torsional vibration and linear vibration. What's only different is how they vibrate. You got linear vibration, you've got angular vibration. So the last thing that's a really important concept, and I will go into more detail with that, is the mechanical natural frequency versus the torsional natural frequency. In the mechanical natural frequency, your classic equation is square root of k over m. Your natural frequency increases when your stiffness goes up. Your natural frequency decreases when your mass increases. Similarly, your torsional natural frequency goes up when your torsional stiffness goes up, and your torsional natural frequency goes down when your polar inertia increases. So a really important concept, and I'll have a lesson entirely dedicated to understanding the concept of natural frequencies and understanding the concept of resonances. So we'll get into more detail about this. But moving on, a very important concept in torsional analysis is being able to calculate the polar inertia of a shaft and the torsional stiffness of a shaft. So from classic mechanics of solids theory, your torque is equal to your torsional stiffness times your angular displacement, and which is also equal to shear modulus multiplied by the polar inertia times the angular displacement divided by the length of the shaft. And your polar inertia is equal to your density of the material multiplied by pi multiplied by the fourth power of the diameter multiplied by the length divided by 32. And you can derive these equations, and if anybody's interested in how these equations are derived, please feel free to ask me, and I'll be more than happy to show you how to derive them. Also, if you look at any classic vibrations textbook, they typically step through the derivation of these equations. So in case you're looking for any textbook or any reference material, please let me know, and I'll be more than happy to share that with you. Similarly, the torsional stiffness of a cylindrical shaft is then calculated using pi, the fourth power of the diameter, shear modulus divided by 32 over L. So the two things that you can read from this equation is, if you have a shaft and if you want to increase the inertia of the shaft for any particular reason, what do you think would be the best way to increase the shaft? You can increase the inertia of the shaft by either increasing the density of the shaft, or you can increase it by increasing the length of the shaft. But really, the most bang for the buck would be increasing the diameter of the shaft. If you increase the diameter of the shaft by 1 point, you're going to get 4 times, or rather to the power of 4 difference in the polar inertia. Similarly, with the torsion stiffness, if you actually increase the length of your shaft, then you're actually going to drop the torsional stiffness. But if you increase the diameter of the shaft, then you can significantly raise the torsional stiffness of the shaft. And And I'll explain this in some of the further modules why this is important. When we do some of the modeling and when you see some of the results, you'll understand why it'll be important to make some changes in your design phase, to accommodate certain torsional issues that can come up with. So the best way that you can affect your torsional inertia or your torsional stiffness is is by changing your diameter. Okay, so time to get down to brass tacks. I've promised you guys a very hands-on course on torsional analysis, and so far I've only been talking about the theory of torsional analysis and some basic equations and some basic calculations. So I've promised you all a very practical hands-on torsional course, and I'd like to get started with Dyrobes as soon as possible so I can hold your interest and I can show you how useful this tool is from the get-go. So what I have here on the screen is the last slide of this PowerPoint presentation, and I have two equations there. One is the polar inertia of a cylindrical shaft right here, and the torsional stiffness of the cylindrical shaft calculated right here. So let's get started by pulling up Dyrobes, and let's go ahead and calculate these two values, polar inertia and torsional stiffness, of a very simple shaft. So I minimize this and I'm gonna now log into Dyrobes. So go ahead and click Dyrobes, launch it, and so this is the home screen that pops up in Dyrobes. And before we get started on anything, I'd first like us to focus a little bit on some settings within Dyrobes. So go ahead and click on Project up here on the left hand corner and click on Preference Settings. Now under Preferences Settings, all the different graphic settings, the display colors, the post-processor graph settings, the graph labels, all of this can be controlled from this particular menu. What I like to do from the get-go is to change a couple of settings from the default so we can view the models a little more better. So go ahead and click on Model Display Settings, and under the Model Display Settings there's a tab called Description. Make sure it's checked. In my case it is checked, and hit OK and hit Save, and it'll open up a Save As window, and you'll be able to save your particular preferences of how you'd like certain views within Dyrobes. And as we get into more detail, you'll see how this is very useful. So go ahead and click Save, hit Yes, and Close. Alright, so let's get started. So what I'd like to do is show you an example of how to calculate the polar moment inertia shown in this PowerPoint presentation here, and the torsional stiffness of a shaft. So I'll minimize this, and Dyrobes is broken down into two components per se. One is the pre-processing or the modeling, and the other is the post-processing. So when we start building the model, we come under the pre-processing approach, and to build a simple shaft, you start with clicking on Model, click on Data Editor. So what it does is it pulls up a window with all the different options on how to model specific aspects of the rotor. So for example, you feed in your units, you feed in your material properties, you develop your shaft elements, you put in some discs. If you want to select some bearings, you can. If you want to add some foundations, you can. So up here we have several other options, and we will be focusing most of our work in this course on these lower tabs here and on this main torsional / axial tab. So let's get back to the modeling of this example, and go ahead and click on the units / description tab, and what it has here is a display of the units that you'll be using for this particular model, and also what the description of this model is. So first thing I like to do is to set my units, and you can see Dyrobes has 4 different unit systems that we can use. One is the classic consistent English units, which is seconds, inches, pound force second square over inch. Engineering English, which is pound force and pound mass being the key differences, and then consistent SI units with meters and kilograms and newtons, and engineering metric units, which replaces meters with millimeters. So depending on what your preference is as far as units go, you can pick either of these options. I personally like to work in consistent English units because that's typically what we use here in the United States. Now, in certain cases, when you're dealing with some equipment that is sold in Europe or produced in Europe, then you can go ahead and click on engineering metric units. Now, there are some ways of saving your files from metric to consistent English or consistent English back to metric. It's very easy to save back and forth. So, for example, if you're sharing models across continents and you wanted to and your preference is working in consistent English while your counterparts in Europe are have a preference of working in metrics, then it's very easy to save a Dyrobes file or into a different unit system from the unit system that you started. So without much further ado, I'll go ahead and click on consistent English, and under the description context I'll give it a description. So let's call it example 1, calculating inertia and torsional stiffness of a simple shaft. Alright, and click on save, and it'll open a save as folder window for you, and I will be saving all of my materials on my desktop. So under torsional course materials, example 1, and let's call it example dash 1. Click save, and we're good to go. The next step is to select the material that we'll be using for our particular shaft. So click on the material tab, and you have an option of selecting, looks like 201 materials in this particular model. Now typically some of the more complex models that I've built, I may have at most 8 or 10 materials. For this particular example, let's just select material 1, which will be material number 1, and let's pick typical steel and go ahead and click select. So what it does is it populates this first row, and the mass density that it calculates is 7.32 e to the negative 3, I believe, and it leaves the density. Again, don't forget we're dealing with consistent English units, so we have density in terms of pound force square over inch raised to 4 instead of the classic pound mass over inch cube, and the shear modulus 1.154 e to the 7 psi, pound force over inch squared, and the elastic modulus. And after selecting the material, go ahead and now click on shaft elements, and this here is the meat and potatoes of Dyrobes. This is where you build your rotor. Dyrobes follows a sort of a finite element approach. If you've had any experience modeling using ANSYS, then sort of think about what you do. You select your units, you select your materials, and then you do your pre-processing, build your model, and then you assign your elements. So we're sort of following the same basic approach, and in order to start that, you first develop your element. So in this case we're only going to need one element, since we're just trying to check the torsional inertia and the torsional stiffness calculated by Dyrobes, and we're then going to go ahead and compare what we calculate with respect to a hand calculation. So without much further ado, under the element column right here, click there and hit element number 1. So this is the first element, so it'll be element number 1, and under sub, click on type in 1 as well. Now what the sub is it's sort of a, for very long rotors for very big models, it's very useful to use sub elements because it helps with reducing the computation time. In our particular case, since we're building one element, it doesn't matter, so you just keep one sub element. Now, under material, type material 1, and I'll explain why you type material 1 in a second. Under level, type 0. Now you type 0 because what the level tab does is it actually gives you a vertical distance. So in this case, since we're building a simple shaft, we're not going to be adding any shaft above the or below the shaft that we're working with, so ignore that and leave that at 0. So our example shaft is going to have a length of 10 inches, and leave the mass ID, which is inside diameter. Since we're modeling a solid shaft, there's no inside diameter, so in this case the mass inside diameter is 0. Now the mass outside diameter, make that 8 inches. Similarly, since there's no inside diameter, there's we leave the stiffness ID as 0, and the stiffness OD, because the diameter of the shaft is 8 inches, the stiffness outside diameter is going to be 8 inches. And then you can leave any comment that you like. So in this case, we'll just call it shaft 1. Okay, so hit save, hit close, save data before exit, click yes, and there you go. This is our first shaft that's been modeled in Dyrobes. Notice up here up top we have example -1, calculating inertia and torsion stiffness of a simple shaft. So what it did here is it pulled the description that we typed in, and secondly, if you go back to shaft elements where it says material 1, this material 1 corresponds to material number 1 that you input earlier. So closing this, close, hit save, this is your first shaft. Now what I'd like us to do is, before we move ahead, I'd like us to carry out a hand calculation of this exact shaft that we've modeled, calculate the torsional inertia, calculate the torsional stiffness. From our hand calculations, I'd like to then compare those numbers with the numbers that Dyrobes calculates, and that'll give you a really good understanding of how to calculate torsional inertia and torsion stiffness. So what I did here is I created a very simple Excel spreadsheet, and what I have are the two formulas, polar inertia and torsional stiffness. So rho is the density of the material, d is the diameter of the material, L is the length of the material. Similarly, G here is the shear modulus of the material. And in our model, we have the diameter set as 8 inches and the length set as 10 inches, right? And the density and the shear modulus, I pulled these out of the values that Dyrobes gave us. So let me show you where we pull them. So if you go back to the Dyrobes and click on model, open data editor, and click on material, there's your mass density, which is in pound/4 /s² over inch to the power 4, and your shear modulus, which is in psi. So I pulled these two values and I pasted them over here, and then I ran this calculation, and what I'm calculating is 2.9474 pound force inch second squared, and the torsional inertia, which is pound inches per radian. So these are the two numbers that we're looking for from Dyrobes to calculate for us. So let's go back to Dyrobes and I'll show you how to calculate this in Dyrobes. So pulling our example 1 model back up, click on model and scroll over to model summary. Now I love the model summary. It's really great because it gives you an exact idea of what parameters you've put in the model, and it gives you all the pertinent information about the model, that you need in order to make sure that you have an accurately modeled rotor. So go ahead and click on torsional vibration, and it'll pull up this OT0 file. And what it is it's a text file that describes all the different parameters of the shaft that we just modeled in. For example, we have material property number 1. The mass density is this right here. The shear modulus is presented right here. We have one shaft element which is reflected right here, and you can see that we have a length of 10 inches, an outer diameter of 8 inches. And so what Dyrobes did, it went in and it calculated your axial stiffness, and it calculated in your torsional stiffness. And this number right here is your torsional stiffness. So I'm going to copy this number here and minimize this window and open up Excel, and I'm going to paste it right next to torsional stiffness, and there you go. You have the numbers match. Similarly, going back to the OTO file, we have the polar inertia calculated, so which is right here, and I'm going to copy this number over to compare it with our hand calculations. So copy and open up Excel, and there you go. So that shows you that this is the first, if you will, validation of Dyrobes, and it compares very well with hand calculations. This concludes our first lesson in module number 1. The main point of this module was to introduce you to Dyrobes and to also put some of the theory together with some of the practical application. You know, we typically try to always validate any new software or any tool that we use, and you know, starting off with some hand calculations and then validating with the software starts building your confidence in your modeling capability and also your confidence in the software. So the next lesson I'll be teaching how to calculate torsional natural frequencies and how to calculate mode shapes, and what the meaning of a torsional natural frequency is, what the meaning of a mode shape is, and why they're important to us in torsional vibration. So see you in the next lesson.